Next we have number 8, and this one also starts just like number 6 that we saw in the previous video. Let A, B and A alpha denote subsets of a topological space X, where A alpha is a family of sets. We have to determine whether some equations hold, and if a given equation does not hold, we have to determine whether we can replace it with one of these two inclusions. There are three parts. This is part A, which states that the closure of A intersection B equals A closure intersection B closure. The solution starts like this. By part A of exercise 6, the closure of A intersection B is contained in the closure of A and also in the closure of B. You know how? Because A intersection B is contained in both A and B. So that is why this closure is contained in the intersection of the closures of A and B. But we don't have equality in general. The equation is not always true, although we have this containment. To see why, we take the space of real numbers with the usual topology, in which say A is the open interval 1, 2 and B is the open interval 2, 3. Let's first see what is A intersection B closure. Because A and B have no intersection, that's the closure of the empty set, which is the empty set. However, A closure intersection B closure is what? A closure is the closed interval 1, 2 and B closure is the closed interval 2, 3. This intersection is not empty. It has this single point 2. So you can see that in this case, these two things are not equal, which means that although we have this containment, but the reverse containment is not true always. Next we have part B. In part B, it's exactly like part A. The only difference is that now we don't necessarily have only two sets, but rather a general family of sets, A alpha. And the solution is similar. Exactly as in part A, we have part A means what we saw just now. We have this containment. And here also, equality is not true in general. What's the counter example to show that this is not true in general? This is the counter example. Your family can consist of two sets, this A and this B, in your space of real numbers. Their equality fails, so that means equality is not true in general. Next, part C states that A difference B closure equals A closure difference B closure. Let's start the solution by taking any point A in A closure difference B closure. That means A is in A closure and is not in B closure. Because A belongs to A closure, every neighborhood of A intersects capital A, and because A is not in B closure, there will be some neighborhood M of A which does not intersect B. So, M intersects A difference B. This intersection is non-empty, but M does not intersect A intersection B. This second difference is empty. But why? Let's see. We can understand the situation pretty easily using this Venn diagram. Say this is your space X expressed as a rectangular region. Okay. In X, you have the set A and you also have the set B. There is possibly some intersection between them, so this is a general situation. Now, what is the condition? The condition is that every neighborhood of the point A intersects capital A, and M is one such neighborhood, this region within this wavy closed curve. Okay. It intersects A because it's the neighborhood of that point small a, but at the same time it does not intersect B. So this region cannot intersect this. So then what is happening? This region intersect this other region A difference B, which is expressed here using this horizontal bars. Okay, this region. So that's why M is intersecting A difference B. But of course, M does not intersect this common region because it does not intersect B. That is why this second intersection is empty. Now, if the point A has a neighborhood N which does not intersect A difference B, then M intersection N is a neighborhood of the point A satisfying the following condition, that it does not intersect A. It's not immediately clear why this is a consequence of these things. Let's first make it clear. Suppose this is not true. This intersection is non-empty. Then that means there is a point in this intersection. Choose a point B in this intersection. Okay. Then B in particular belongs to N intersection A as well. Alright. However, N does not intersect this part of A, that is A difference B, and this point B is inside N as well as A. So because N cannot intersect A here, so that means N has to intersect A in the other part of A, that is A intersection B. So this common point B has to lie there in A intersection B, which means that in particular B belongs to B. But at the same time B is also in M, and this is the problem because recall that the original choice of M was what? M was a neighborhood of our point A which does not intersect B. There is no common point. That is why this cannot happen. This has to be empty. Okay, so that means this has to happen. But this itself causes a problem. Because this now contradicts the fact that A belongs to A closure. Why? See, because A belongs to A closure, every neighborhood of the point A has to intersect the set capital A. But this is a neighborhood of A which does not intersect A. So there you have a contradiction. Do not get confused with this entire thing, okay? We wrote this part based on the assumption that if something happens, then this happens. And then we found out that this cannot happen because something else goes wrong. So the fact that we have this equation is true conditionally. If this is true, then this is true. But it turns out that actually this cannot be true. So now we will conclude that because of this contradiction, this cannot be true. That means we can have no such neighborhood N which does not intersect A difference B. Or in other words, every neighborhood of A has to intersect A difference B. There is one more subtle thing. It's not subtle actually, it's just an observation. Because M and N are both neighborhoods of A, so they are basically what? They are open sets containing A. So their intersection is also an open set which contains A, and that is why this is a neighborhood of A as well. But now what can we write from this? This, that the point A belongs to the closure of A difference B, because every neighborhood of the point has to intersect A difference B. That's why. But then what have we achieved? Recall that the point A was any point in A closure difference B closure. So we have found that any such point has to lie in this set. So this is a subset of this. But the reverse containment is not true. That means we won't have equality, for which we now have to produce a counter example. We take the same counter example that will work in this case as well. Same space of real numbers. A is the open interval 1, 2 and B is the open interval 2, 3. Then let's calculate this difference. A closure is closed interval 1, 2 and B closure is closed interval 2, 3. So if you remove this from this, only the point 2 gets removed. The other points remain. So you get the closed open interval 1, 2 as this set. Whereas if you calculate this, what is ordinary A difference B? Because A and B are disjoint, if you remove only B from A, nothing actually gets removed. A remains in its entirety and its closure is the closed interval 1, 2. So you can see that they are not equal. In fact, this is the proper subset of this. So that subset relation remains, but equality does not happen in this case. So that means equality is not true in general. Let's see another one, number 10, where we have to show that every order topology is Hausdorff. So we start the solution by taking an ordered set and let tau be the order topology. What is it that we have to prove? We have to prove that if we choose two distinct points in X, then they can be separated using disjoint neighborhoods. That's what Hausdorffness is. So we take 2 points X and Y in X which are set distinct. Because we are in an ordered set, what does that mean? It means that either X is less than Y or Y is less than X by comparability property of linear order. Okay, you recall that thing. So we assume without loss of generality that X is less than Y. Now we have to find a neighborhood of X and a neighborhood of Y which are disjoint. Now if there exists a point Z in X such that Z is greater than X and less than Y, then we can consider these two rays, open rays. One of them is minus infinity comma Z, the other one is Z comma infinity, both of which belong to the order topology. That means both of them are open sets. Why do they belong to the order topology? Recall that this type of things form a sub-basis for the order topology on an ordered set. Okay, so they are open, and clearly from these inequalities we see that X belongs to this, Y belongs to this, and they are disjoint also. So here we have found a neighborhood of X and a neighborhood of Y which are disjoint. But what if there is no such point set? Then it's not necessary that our ordered set should be dense like the real numbers. For example, between any two real numbers there is a third one. You already know this fact from analysis. Our ordered set may instead be like the integers. Say if your X is like 1 and Y is 2, then between them there is no integer. Even in this case we can do something. You consider these two rays, minus infinity comma Y and X comma infinity. They are also open in the order topology. Now this is the neighborhood of X. Why? Because X is less than Y, and because of that inequality this is the neighborhood of Y. And what is the intersection of these two? That's the open interval X comma Y, which is empty because there is no point between X and Y. So again you have been able to separate X and Y using disjoint neighborhoods, and that's why our ordered set with the order topology is a Hausdorff topological space.